Good morning, everybody. Today we're going to be talking about enthalpy. Enthalpy is the heat content of a system at constant pressure. So change in enthalpy is delta H. I remember that because this delta symbol, the triangle, is for change. So delta H is going to be H of products, or what we get finally, minus the H of reactants, which is what we have initially. So when we're talking about enthalpy, we're going to be talking about things like the heat, obviously the heat content of our system, but basically how heat is changing over the reaction. Are we having heat released in the reaction, or are we having heat absorbed in the reaction? And really how much heat is released in the reaction, or how much heat is absorbed in the reaction. So one thing you need to understand is that when heat is absorbed in the reaction, that's called an endothermic reaction. And when heat is released by the reaction, that is called an exothermic reaction. So let's go into a couple of examples. So our first example is carbon plus oxygen yielding carbon dioxide. And you'll notice right here I have plus 395 kilojoules of energy. So that means that our reaction is releasing energy. That makes it exothermic. So you might be wondering, well, why is it exothermic? The reason that this reaction is exothermic is because it is making new bonds. So these two things are coming together. Whenever we are making connections and making new bonds, that is exothermic. So we are making or releasing energy. You might also wonder why I have plus 395 here and minus 395 here. This is in terms of the reaction. So we started with more energy here and then we released it. Okay, so this is a minus 395. Also notice in terms of our reaction, it's going down. So we should have energy over on this side. Okay, overall, energy is going down. So this is an exothermic reaction. This reaction, notice what side the energy is on. We have plus 176 kilojoules, but it's on the left-hand side of the reaction. Okay, it's on the reactant side. So in this reaction, where we have calcium carbonate plus 176 kilojoules yields calcium oxide plus carbon dioxide. Okay, in this reaction, we have bonds breaking. If we have bonds breaking, that requires energy. We have to put energy into that in order to break those bonds. So that is going to be endothermic. All right. And notice also over here that we have plus 176 kilojoules. Another thing to observe is that our reactants are at lower energy than our products. Overall energy is going up. So that's endothermic. So what that means is that our reaction has absorbed energy. Absorbing energy means that it's endothermic. Okay. So a couple things to get closer to the calculations that you're going to be doing. So this video is just informative. The next video is going to be in terms of the calculations that you're going to be doing. So heats of combustion. Heats of combustion are the heat from the reaction that completely burns 1 mole of a substance, specifically at 25 degrees Celsius and 1 atmosphere of pressure. Combustion is always exothermic. If you think of combustion when you're burning something, if you light a candle, if you have a backyard fire, all of those are combustion reactions. They're releasing heat and they're always exothermic. So our delta H of combustion formula is delta H of combustion is equal to kilojoules divided by moles. Okay, so you will notice as I go through the rest of this that all of the formulas are very similar. I'm just going to be changing a few specific words. All right, so the molar heat of fusion, is the heat from the reaction that completely melts. And we take out that 25 degrees Celsius because melting doesn't always necessarily occur at 25 degrees Celsius. They're not always exothermic. And now we're going to call it delta H of fusion. All right, I should spell fusion correctly. All right, so heat of fusion is the heat from the reaction that will completely melt 1 mole of a substance at 1 atmosphere of pressure. And notice our formula is basically the same. I just changed the subscript here to delta H of fusion. Another thing that you should note, when we're talking about melting, the opposite of melting is freezing. So, equal but opposite, we're going to have the delta H of freezing. So if you're ever asked to calculate the delta H of freezing, you're going to use the delta H of fusion, but negative. Oops. So the delta H of fusion is equal to negative the delta H of freezing. And one more, we have the delta H of vaporization. All right, so the heat of vaporization is the heat from a reaction that completely vaporizes. And it's not really a reaction that's vaporizing it, because vaporization and even melting wasn't a reaction. But it's the heat that will vaporize a substance at 1 atmosphere of pressure. So delta H of vaporization is still going to be calculated using kilojoules per moles. And just like melting, it has an equal but opposite. So it's going to be negative delta H of condensation. I'll write that one in blue. So again, if you're asked to calculate the delta H of condensation, it's going to be negative the delta H of vaporization. Equal but opposite. So to bring this back to what we were talking about last week. So we have our heating and cooling curves. So our cooling curve looks relatively like this, depending on what substance you're looking at. A heating curve looks relatively like this. Again, they're going to change a little bit depending on your substance. However, you need to know where delta H is located. All right, so delta H is going to be on these straight lines right here. And that's why we were just talking about melting and vaporization, freezing and condensation. Another thing you need to understand, notice right here where we have our first delta H. Okay. We would be going from a gas to a liquid. So from a gas to a liquid would be condensation. And we would be putting things back together. So this would be exothermic, putting things back together. So both condensation and what we have right here, from liquid to solid, okay, and I'll label those. Gas to liquid to solid. So this would be delta H of condensation. This would be our delta H of freezing. Delta H of condensation because it's going from a gas to a liquid. This would be delta H of freezing because it's going from a liquid to a solid. And these are going to be exothermic. Why exothermic? Remember from our previous discussion, overall, from reactants to products, energy is going down. Okay? From gas to a liquid, energy is going down. Also, think of it like this. Things are coming together. Particles are coming together. From gas to a liquid, we've got things spread apart, and then they're coming together. So that would be exothermic. They release energy when we start to put things together. The opposite is happening over here on our heating curve. So our two locations where we have, or where we need to calculate delta H. It's right here, okay? So going from a solid to a liquid, that would be our delta H. Remember, they called it delta H of fusion, not delta H of melting. So this is our delta H of fusion. This is our delta H of vaporization. And delta H of fusion and vaporization are both going to be endothermic. Overall, our energy is going up for the reaction. It's absorbing energy. It has to absorb energy in order for something to melt. Think about, in order to get a solid to go from a liquid, you have to put energy into it. Same thing from a liquid to a gas. You have to put energy into it for it to get warmer. Think about water. In order to get water to boil or vaporize, you have to put heat into it. So that's going to be endothermic. All right, so that's it for our enthalpy informative video. The next video is going to be how to do some problems. And I hope you've enjoyed, as always.